Now, in the next two videos, we're going to be introducing very new concepts that don't make sense now, but they will end up and make sense a bit later. So these are very, very important concepts because they explore ways or help you better understand why gel is being used in the first place. So that's why we need to cover these concepts a little bit so that we can be able to understand how or why gel is put on the skin to begin with. Okay, the first concept we're going to explore is known as specific acoustic impedance. You've never heard of this before. If you've done this topic before, you've probably heard of it. It's a bit of a recap. But this is a new concept that we need to introduce. Basically, specific acoustic impedance consists of three words: specific, acoustic, and impedance. The word specific refers to very explicit, right? In relation to a particular medium, e.g., particular medium. Acoustic refers to sense of hearing, sense of sound, signs of sounds, right? So hearing, forget a little G over there. Impedance refers to the opposition to the flow of anything, right? To the motion of anything. Let's oppose that. So you can sort of think of specific acoustic impedance as the opposition to the movement of sound in a particular medium. So this is a little animation that I gave you guys. So you can sort of think of how can we be able to oppose the flow of ultrasound. And that you can sort of think of that as specific acoustic impedance. So if you want to compare two mediums, right? You have medium A and medium B. You want to look at those mediums in relation to how sound travels in them. You can look at the mediums themselves. That is the density of the medium. So if you have a person A and you have a door and you run towards that door, if you're able to enter into the door, it can either be because the door is thin, right? It's not that very thick. The density of the door is very little. But if you're not able to pass through, it means that the door is either very dense or it's very, very thick. So the opposition to your motion is determined by the thickness of the door. In the same manner, the opposition to the motion of sound is opposed by the medium itself. Or you could also look at the speed of the sound itself. So you can look at the speed of the sound as it's moving, or you could look at the density of the material itself that you're moving through. And those are the two factors that could affect how that sound is opposed to motion. So if it's very slow, there's going to be an effect in how it's going to be opposed. If it's moving fast, there's also going to be an effect in how it's going to be opposed. So below is the required Cambridge definition of what specific acoustic impedance actually is. So it's defined as the product of the density of a medium and the speed of ultrasound in that medium. So be very specific, guys. I don't see why you need to redefine these equations. Use it as it is, right? The product of density and the speed of ultrasound in that medium. Okay. So here's this little guy holding up this equation over here where Z is the specific acoustic impedance, rho is the density, and C is the speed of sound in that medium itself. Okay. Why is this important? Because the greater the difference in acoustic impedances of two materials. So if you have one material, which is air, let's assume in this example, the material is air. Then you have another material, which is over here. Let's assume it's skin, right? If there's a very large difference in acoustic impedance, you can think of it as you have an incident wave like this, okay? An incident wave like that. And it's going to try to move into skin. But then realizes, you know what? This is so difficult. I'm never going to enter into skin because it is a higher specific acoustic impedance. Why bother? Most of my waves are going to be opposed either way. It's going to struggle entering into skin at this point. It's going to be like, no, what, screw this, right? And it's going to get reflected. So most of it will be reflected back, and some of it that can be able to pass through will be able to pass through, right? And you can therefore be able to realize that, hey, a lot of the waves are actually reflected if there's a very large difference in acoustic impedances. So the greater the difference, the more the reflection that will be present. And the smaller the transmission, this is transmission over here, the smaller the transmission that will also be observed, right? So we're going to go through a couple of examples in the next video to make sure that you've truly understood what intensity, to make sure that you've truly understood what specific acoustic impedance actually is.